Before an AI agent can act on-chain, it needs a map of the world it's entering: blocks, wallets, keys, data, and transaction risk. In this module, we'll build that mental model from the ground up. So far, we've built the agent foundation: tools, planning, memory, workflows, and safety. Now we're applying those capabilities to blockchain systems. Before an agent can sign transactions or call contracts, it needs to understand addresses, wallet state, reads, writes, gas, and how on-chain actions change shared state. At its core, a blockchain is an application state machine that no single company owns. Its state includes balances, ownership records, contract variables, transaction history, and event logs. A transaction requests a change to that state, such as sending tokens or calling a contract. Validators order those requests into blocks, and nodes update to the same result. For an AI agent, the chain is both a source of truth and a place to act. Another way to view a blockchain is as an ordered history. Transactions are bundled into a block, and each block points back to the one before it, making past changes increasingly difficult to alter. Consensus is how validators or miners agree which proposed block is valid and should come next. Finality is the confidence that a transaction will stay recorded. For high-value actions, agents should wait for enough confirmations before treating the event as settled. Each blockchain network is a separate operating environment. Ethereum mainnet carries real value, so mistakes are expensive and controls must be strict. Testnets are practice spaces, useful for experiments because the assets are not production money. Layer 2s often offer lower fees and faster execution, while app chains may define their own rules, assets, and contracts. For an agent, the first safety question is always, which network am I connected to? In blockchain systems, an account is the identity that can hold assets and change state. An externally owned account, or EOA, is controlled by a private key, like a wallet. A contract account is controlled by code. Both are identified by public addresses, which can be shared safely. For agents, the key distinction is authority. They may inspect any address, but they can only act with valid permission to control or call that account. A public address is a useful starting point, but it is not identity by itself. From one address, an agent can inspect balances, token holdings, NFTs, approvals, transaction history, and contract interactions. Those signals reveal behavior and risk, not necessarily who is behind it. A human company or bot may control many addresses. The safe rule is simple: analyze activity carefully, but avoid claiming attribution unless another verified source supports it. On-chain state is the blockchain's current record of truth. Some state, like ETH balances, is tracked by the network itself. Other state lives inside contracts. ERC20 balances, NFT ownership, allowances, permissions, and protocol positions. So an agent cannot just ask, what is in this wallet? It has to ask the right contract on the right chain at the latest reliable block. Good decisions start with reading the correct state before taking action. A transaction is an instruction packet signed by an account that asks the network to update state. It includes the sender, the recipient if there is one, any value, optional data, a nonce for ordering, fee limits, and the signature proving authorization. With plain value, it becomes a transfer. With encoded data, it becomes a contract call. For agents, careful construction matters because once accepted, blockchain changes are difficult or impossible to undo. It also helps to see a transaction as a life cycle, not a single send button. The agent can form an intent and build the transaction, but signing is the trust boundary. That step should require user approval or strict policy checks. Once signed, the transaction is broadcast through an RPC provider or node, waits pending in the mempool, and may be included by validators. The receipt becomes the source of truth: success, failure, and gas actually used. Gas is the meter for execution work. A transaction sets a gas limit, which caps how much work it can consume. Fee settings determine what you pay per unit, often including base and priority components. Estimated cost is gas used times fee per gas. Complex contract calls burn more than simple transfers. For agents, the pattern is estimate first, compare against policy, and refuse or escalate when fees are too high. Being included in a block does not always mean the goal was achieved. An agent might submit a token swap using an old quote. Before execution, the price moves beyond the allowed slippage, so the contract reverts. The intended swap never happens, but validators still spent computation, so gas can be charged. Because ledger history is generally irreversible, the right pattern is prevention. Simulate the call, validate parameters, check deadlines and balances, then apply policy before writing. A useful mental model is observation versus action. Read operations ask the chain what is true: balances, contract values, logs, or past transactions. They usually need only public RPC access and no private key. Write operations try to change what is true: sending funds, approving spending, minting, swapping, or calling state-changing functions. That means signatures, fees, monitoring, and strong approval guardrails. For agents, every write should be treated as a controlled action. For Onchain agents, the key design pattern is separation of powers. Reading chain data and producing recommendations should be isolated from tools that can write transactions. Before any write, the agent should validate the network, address, and contract. Then simulate the call, estimate fees, apply policy limits, and request user approval. After submission, responsibility continues. Track whether the transaction is pending, confirmed, failed, or replaced, and report that state clearly. You now have the mental model. Blockchains hold shared state, transactions request changes, and accounts give agents an identity to observe or act through. Reads are usually safe. Writes demand signatures, gas, and safeguards. Next, we'll add wallets, keys, RPCs, smart contracts, and testnets, so agents can operate confidently.